when you take a popcorn, put lights to dusk, and prepare for the show. Anyone try to enjoy next homework? Just did you read what it is? Okay. Yeah. Previous two homeworks were kind of staying behind the lecture material, and now we are at the edge. It's not easy to match them ideally. Maybe one day homework will go a little ahead of class material, but now we are at the very right place. Do you know how to? Well, please lift hands if you have installed MATLAB on your personal laptops or desktops. Oh, okay.
Oh, okay, right. I thought you said haven't.
That's really great. Then you become independent from auditorium or instructor. It's good. So it is recommended. If you didn't, and we have plans for presentations on coming Friday, when you are coming to the class, the lab tonight, try things that you're going to present, make screenshots, and copy paste them into PowerPoint, and then send this PowerPoint to us. Right? I know that it is trivial things, but just if someone wants to come to Blackboard and MATLAB is software package, no, per PowerPoints. So the goal of the course is to do what? Huh? Yes, yes. I'm so happy that no one asks answers to torture young minds. Predict the future in a sense of predict outcome of a measurement. So we do not have details, we do not have specific experiment yet, but we will try to make effort towards predicting properties of real existing molecules and materials. Well, with some limitations, maybe we will not reach the top of the mountain on this road, but all efforts are oriented there. And before, all our efforts were on the background. It's very hard to convince anyone, especially in chemistry, that rubbed electron is a very realistic system. So it's good that we learned something, but it is on the background. So if electron hasn't been rubbed, okay, so it's all material, that's what we present, it's homework. Now, if the electron is not rubbed, what happens to electron? What does it do in real life?
Proton.
Yeah, meets its favorite proton. What else an electron can meet? That's good. I like your thought. So there is a little proton, and this electron wave function collides and maybe get captured by a proton. Right? This is most simple and natural train of thoughts for, how to say, traditional PChem and quantum courses. Then you get hydrogen atom. But no, we will not do it because it is, if we just tell fairy tales, it will not help you. You already know them. Like hydrogen atom, sp, d orbitals, right? It's not much, but if you go into full details, it is the really advanced math that we are not ready yet. So we'll get to something maybe more complicated philosophically, but much less challenging mathematically. So we'll Well, I know that sometimes you feel a little exhausted of exercises that we do, but I'm trying to build it so that we do not run up too fast. So electron E minus can be kept by proton to form hydrogen atom. Or it can be any positive nuclei for electron wave function being kept and form this S, P, or D orbitals. Right? Electron likes to be attracted. Right? So if there is some positive charges, electron will go there. Electron doesn't like to be repelled as any of us. So if it meets some negative charge, if it see another electron, they will repel. Right? What is nanoscience? Well, it's in use, so you should have an idea. What does mean nano?
Very small.
Yes. What does it mean very small? Like atom is very small. Is nano smaller than atom or larger than atom?
Roughly the same magnitude.
Well, maybe 10 times bigger or 100 times bigger. So there are different, like, you already got an idea from our previous considerations that quantum theory methods same as weapons in computer games. You select different methods against different monsters. So, and on the account of monsters, we have different molecules or different materials. So there are different levels of materials and molecules which will need different methods. So one can think of atoms, which may be too boring for chemistry, then molecules, which is true chemistry, and then there is a next layer when molecules assemble to each other in polymers, or if it is something inorganic, there is a formation of crystals. You can have solid-state chemistry, right, for crystals or surfaces. But nanoscience is when you deal with objects that are smaller than crystal but bigger than molecule, roughly. Right? So the order of maybe 1 nanometer or 10 nanometers, therefore nano. What is nanometer? How much?
It's like 10 to the negative 9, right? 10
Yes, yes, yes. And what is the size of hydrogen atom? Is it bigger or smaller than nanometer? So, like, if your electron is getting captured by a proton and start circling on the Bohr orbit, of course we know that it will be distributed stuff, but what is the approximate Bohr radius, the distance from proton to an electron? I don't care, but you may. If you are going to be more practical and applied, involved in practical applied research, industry, teaching, you may find this a number. Any guess?
-12. 10 to the -12
Of what?
meters.
Okay, 10 to the -12 will be picometer, right? So 1,000 times smaller than nanometer. No, I don't have any interesting logical stories to argue with it, but it will, picometer, 10 to the -12, is approximate elongation of atomic bond. If you, let's say, have H2 molecule, and then it slightly elongates, then it is by picometer. But distance between electron and proton in atom, or distance between, there is a number that you may know. What's the distance from hydrogen to oxygen and water molecule? What were you doing in freshman chemistry?
Occidental reverse order.
Approximately. So 10 to the minus 12 is too small. 10 to the minus 9 nanometer is too large. Yeah, perfect. Please remind me your name.
Michael.
Michael. Now we are doing traditional physical chemistry. So 10 to the minus 10 meters is 1 angstrom, here is little circle, and it is a standard units of measurements for atomic and molecular stuff. So it is 1 nanometer is 10 angstrom, and Bohr radius distance from proton to electron is about half of an angstrom, 5 angstrom. And typical interatomic distances are of the order of 1, 2, in rare cases 3 angstroms. So about 2 angstroms is typical interatomic distances. For carbon, oxygen, it's about 1.5. For hydrogen to oxygen or carbon, it's about 1 angstrom. It could be a little less, but if you tell 1 angstrom, it will be qualitatively correct. Excellent.
So that angstrom is measuring from the nucleus to the nucleus.
Mm-hmm.
Okay.
And from nucleus to electrons, 0.5. Very roughly. We're not caring for 5 digital 6 feet. Okay. So if you do have an object of a size, well, typical molecule is maybe less than 1 nanometer. Then, and if you have an object that, like stuff that consists of packed atoms and chemically connected, of the order of like 12 angstroms, 2 nanometers, it will be a typical thing for nanoscience. Okay? Especially for little pieces of crystals, known as quantum dots, but anything of this size. So, what are the feelings of an electron when it exists inside a nanostructure? So suppose you have a molecule, or better, I like more nanocrystals, which are surrounded by vacuum. So would electron be happy to go outside of a molecule? No. You can force an electron to leave molecule by ionization, by exciting it by light, or by putting it into analytical chemistry device for ionization, right? But typically it is neutral. It means electrons do not want to leave the structure. What does it mean? I'm trying to just, without any equations, debate the simple logic. So electron likes to be attracted, doesn't want to be repelled. So if there are nuclei, so everywhere, if you have chemical structure, we have positive nuclei, protons or whatever, carbons, maybe gold ions. Electron likes to rotate around them or jump between them inside the structure. As soon as it reaches the border, it feels that it's not very comfortable there. It wants to return. Okay? That's the main idea. And what is the name of the chapter that we are starting? How would you call it? I know it is. I'm jumping in logically, but what would be, if you were exposed to any quantum theory or physical chemistry before, what's the most favorite object?
Electron in a box.
Yes. box, not a FedEx package, but box. So we will, thank you. Well, it kind of trivial, but very useful. If you know from our previous considerations that making any calculations and logical steps, we do need to formulate Hamiltonian composed of kinetic energy and potential energy. Potential energy is just potential, how well electron is attracted or repelled to anything. Right? If we do true potential for the ion, it will you cannot do one-dimensional. It is essentially three-dimensional, and this potential V will be 1 over R. So if we insert this 1 over R in our Schrödinger equation and try to solve it, I assure you it is not easy. So we will try to avoid it, just for sanity of our brains. But in case you do have many atoms, it's time to focus. Too blue. But if you have several ions stick together, and you know definition of a molecule that one is getting in high school or when you start chemistry in middle school, it's a collection of positive ions and negative electrons put together through some chemical bonds, right? So if you have ions put together, the net potential that they exert on the electron is not 1 over R or something similar, but they kind of average together. And as a very rough approximation, so anytime you cannot solve mathematical problem, you simplify it and tell it is my approximation. So you can approximate that so if you put them together, these sharp edges disappear, it becomes continuous. And as an approximation, one can tell, okay, let's think that here it will be just something very low, constant, and here it will be just 0. So we approximate set of positive ions attracting an electron as just a region of space with low potential energy and region of space with high potential energy. And then we need just size and shape of the structure that you described. So sometimes if you are really picky, you can tell like it's very far from the molecule. But we cannot do right now more complicated things. This was a point of view in like 30s, 40s, 50s, 60s, but recent years, suddenly one has realized that this approximation gets recent 20, 30 years, that calculations computed under this approximation predict really well several classes of materials. So there are classes of molecules and structures that do not need detailization about positions of ions and can be a lot of properties can be estimated just on the some basic information about size and shape. And this area is nanoscience. So any can you design any examples of a structure that can be described by this picture? I know that Ben may have answer. I saw him practicing some structures. Anyone except Ben? Do not hesitate. There is no punishment for wrong answer.
Are you talking about the one with the like kind of?
Which molecule or which structure can be approximately represented by this potential? Like last year at the same day, same time in the same room, Chris, who is now doing research at Dr. Parent lab, told like, I like gold. It can be a line of gold atoms set in one after another. Can it be? Yep. So it can be a homogeneous set. If you know that several atoms like to stay together in a structure, why not? What else can it be?
Silver.
Very creative, yes. Anyone is planning research in polymers, coatings, or Dr. Seth Rasmussen lab? Okay. Good. Excellent. So, what are conjugated polymers? You know, there are polymers like polyethylene for shopping bags, and there are polymers for the OLED TV. Polymers that conduct electricity and emit light, right? So those would be an ideal example of such thing. So the conjugated polymers is a organic replacement of semiconductors. Like typically semiconductors are inorganic and often poisonous, but if you build structure like this, where a polymer is repeated, polymers like repeating monomer ring, and you have alternating single, double bonds, electrons really like to travel. If you have alternating single, double, it's like a wire. It goes without resistance, or with very much smaller resistance compared to regular sp3 single bonds. And I don't know if you do any equations. You do. Which form of government is right now in this country? How would you call it? Yes, good. Which forms of government are available in the game of civilization? If you did play it.
Wow.
Examples.
Dictatorship.
Okay. And so there are different. What were the options for forms of power in ancient Rome and Greece, except dictatorship and democracy? I'm just trying to get a right word.
Like kings and monarchs?
Yes, it is if there is one ruler, right? And democracy, if like we think
Monarchy.
that. Monarchy, again, mono means one. But democracy is when everyone rules. Monarchy, if only one rules. And in between, if only few are ruling.
Oligarchy.
Yes, perfect. I'm so pleased to be in the surrounding of well-educated people. So, mono, demo, and oligo. So now we are making connection between civilization game and physical chemistry or whatever. So if you have infinite number of these units, it will be polymer. If you have only one unit, it will be monomer, single. And if you have like 1, 2, 3, and then terminate it maybe by hydrogen here. So it is neither monomer nor polymer. How would you call it?
Oligomer.
Oligomer, right? So oligomers of conjugated polymers allow electron to travel along this line until it meets the edges. But it doesn't want to go away. So oligomers of conjugated polymers are excellent examples of particle in the box, right? So there is some low potential favorable for them to exist in the middle of this oligomer, and there is something uncomfortable outside of the box, outside of this model. Good? So it is what we've done by now. Schrödinger, Heisenberg, free space, and there will be one electron in one D box, and we will try Schrödinger equation for it. Right? So just a little navigation if you get lost of what we are studying, what's the reason. Good. Okay, this is not a new joke. I was practicing it before. Conjugated polymers. Another, and it could be different. Like one can have unit cells of like 5-member rings with nitrogen or sulfur. It could be just poly-N rings or SN rings. Those all are examples of conjugated polymers. You got some organic chemistry before, right? So you're more well-versed in it. Another thing, I really like repeating this figure, redrawing from year to year, but I really have it. Suppose that you have bulk materials of metal or semiconductor where electron likes to reside inside. And then let's forget about vacuum. Vacuum is too much. Let's assume that we do have dielectric. Examples? Do you know which dielectrics do you know from your common experience? Huh?
Water. Isn't that like
Water is not the best dielectric because it can conduct electricity, especially if you put
copper? Copper?
dielectric.
So I'm saying insulator.
Dielectric insulator.
Plastic.
Okay.
Rubbers.
Yes. Excellent. Yes. What else?
Porcelain.
Porcelain. Yes. Yeah. Where are you?
Mica.
Where are you thinking of going to electrical engineering? You know, like electric transmission lines with these porcelain insulators between wires. Right? What about glass? Does it conduct electricity? Typically, no. What is glass?
It's just like pretty much sand.
Sand, yes. And what is sand?
Quartz.
Silica.
Yes, and silica is like fancy word. What is like? Silicon dioxide, yes. So silicon dioxide is an excellent insulator. In all your cell phones, computers, there are integrated circuits with silica substrate and then either metal or silicon integrated circuits. So suppose that we do have a layer of semiconductor material, very thin layer, surrounded from top and bottom by insulator, right? So from modern technology, it's not a big wonder. We like do deposition techniques, deposit one layer, another layer, third layer, and then this happy electron can move as it wants inside this layer, but really doesn't want to go into insulator, right? And it can go along. If you add system of coordinates, it can go along x, y, but along z axis, motion is not free. So in x and y, it behaves like free electron, almost as in a free space. But in z, there is a it is forbidden to move. Something confines it. Confinement. So this is a best example, well, another good example of particle in the box. So we forget about motion along x and y, consider only motion of electron along the axis in the sandwich. Sandwich, not like bread, butter, bread again, but insulator, semiconductor, insulator again. Right? And the word sandwich is very popular in microelectronics because it is what they do. They do sandwiches of different materials. If you like read Wikipedia on like diodes, transistors, integrated circuits, they will use word sandwich in each one. So motion in this transverse direction.
What does it say after the A?
Semic. Because
Okay.
I'm semiconductor.
And then above that is that dielectric.
Vacuum or dielectric. I wasn't, I haven't been taught to spell words by like D-I-E or pronounce as things. So there are regions of space where it can move, there are regions of space where it can confine. And there are some other examples, like favorite object of Ben, nanocrystal semiconductor quantum theory, where inside semiconductor it can move, and outside there is either dielectric or vacuum, it cannot. But it will be more complicated, like three-dimensional blocks. Right now, we do not want to have hard, complicated, like we will deal only with one dimension. Good. So moves freely in x, momentum on 0, moves freely in y, momentum on 0, and in z, it bounces force and back. And here, so here are examples of atomistic calculations. So I hope that it will be a good illustration to start the subject of particle in the box and see connection between real life and our course with computational chemistry in between. By the way, right now there will be commercial advertisement. If you do not pause in the show for commercial advertisement, if you're not interested, just close your eyes and ears. In the spring semester, there will be offered a computational chemistry course for undergraduate and graduate courses with CHEM364, where everyone will be able, with guarantee, predict properties of any molecule and material. At the end of the course, anyone who performs well is prepares a paper for publication at peer-reviewed journal. End of commercial, and you can guess who is the teacher of the course. So end of the commercial. So here is atomistic model, very much related to integrated circuits made by one of the students in this course several years ago. So this example is dielectric, silicon dioxide, with red is silicon, blue is oxygen. It's always a little crazy color code. And those are clouds of electrons, like electronic orbitals. So if one, there are codes that solve Schrödinger equation and other equations related to it for distribution of this wave functions for all properties. So right now we are doing very civil work because we are intellectually growing. In fact, there are codes that does it for us much quicker. And the observation in doing such calculations that wave functions, electronic orbitals near the ground state when excited will be localized only in the region, in the central region of space, where it is only this, only where there are silicons. And the region of space where there is silicon dioxide, it is very, the electrons would not like to go there. It's just energetically unfavorable. One needs to excite an electron by an energy of about 8 electron volts, which is hard to do. Like the purple, the end of the visible spectrum is about 3 electron volts, right? Around 350 nanometers. And you're happy with nanometers and electron volts, aren't you? Yes? Electron volts divided by 1, 2, 4, 1 divided by electron volts equals nanometers, right? You remember this conversion factor? No? Yes? Lambda equals delta E divided by, no, 1, 2, 1, 2, 4, 1 divided by delta E, right? Lambda equals 1, 2, 4, 2 or 1, I don't remember, divided by delta E. In nanometers. So if you have light of delta E equals 2 electron volts, it will be approximately equal 620 nanometers. I don't care. I want to believe that you know it, but it's not part of the main materials. Useful. So, about 8 electron volts needed to bring electrons away from the central region, silicon to silicon dioxide. So, those humps stay at the points where there are silicons, where the electron like to be around the ion. And if we integrate it over x and y only as function of z, there will be peaks. Here, electrons like to be outside, they do not like. But if you excite it high enough, they penetrate to this forbidden region. But the energy needed to excite electrons in this forbidden region is high. It's like strong, about 8 electron volts. And here is the best logic I can provide. 8 is so big, so that if you rotate it by 90 degrees, it will become huge. Therefore, we will assume that energy needed for electron to go outside of the box will be infinity in what follows. So I'm not the first to make this joke. It is the standard approach in quantum theory. And it is made because all realistic systems have the size of this barrier in some finite values. But again, solving blocks with finite values is much more complicated mathematically. It is so easier to do calculations like pen and paper for infinite values. Therefore, we will assume that there is no force in the universe that will drive electron outside of the box. Okay? So it is an approximation for next 2 weeks. Anyone knows? Oh, lift hands if you do not know Daniel Ramirez. Yeah, do not. Okay, but you can get acquainted. He will maybe show up and sit here. He was here a couple of times. So it is one of the part of his research, and it is very similar to previous figure. So he's doing thin film of semiconductor materials surrounded by vacuum. So I'm showing it because it is like modern research. And Ben does something similar, but for quantum dots, 3-dimensional, which is too far from what we are doing right now. So it is a semiconductor composed of Yes, relevance. Yes. So lead, bromine, lead, bromine. So the scaffold of lead and bromine with also some cesium ions, but you see it is a crystalline lattice with some added surfactants. And the blue blobs are electrons for a certain orbital. So if this is our z axis, and we put here is 0, here is the L capital size of the box, and here we put the p squared, p of x squared wave function squared. You see that here it is 0, 0, 0, 0. Then at this point there is non-zero, 0, 0, non-zero, 0, 0, non-zero, and then 0 again. So electrons like to be inside the thin film. Those are results from atomistic simulations. If we redo it by the means that we are going to practice next couple of weeks, we will get solutions that will look this way. So 0 away, outside of the box, and something non-zero in between. But it is a little mathematical achievement that we can get. So we will get two solutions that will look like this. So it will be a little different from practical, from real life, but main feature of electrons are permitted. They do exist inside the box, not permitted outside. We will get it with high precision, with high reliability, and you'll get some conclusions related to real life. Okay, so if you actually, there are 5 minutes left, but I'm starting the lecture right now. Before it was just belletristics and introduction. So we start dealing with quantum systems by formulating Hamiltonian and solving time-independent Schrödinger equation. So we need to formulate the Hamiltonian depends on kinetic energy and potential. Kinetic energy for one dimension is standard. The second derivative over position with some combination constant, square, mass, minus. And the potential, here is the, maybe last time I'm telling something about physical chemistry for next 2 weeks. The rest from now on will be pure math. I hope you will enjoy it. So before we were setting that outside of the box we have 0 and inside we have something negative. Because the barrier is set, we agreed to have it in infinite. Let's set 0 inside and infinity outside. Okay? So it will be our potential. So inside the box, it will be the same potential as for the free particle. I dot E dot no potential inside and infinite potential outside. You know, some people, especially old people, do not like figures. I've seen, and I hope I'm not yet very old. It's like next 40 years older than myself. I was showing to such people like figures, telling, look at this nice result. I don't understand you. Write an equation. So if you need to write an equation for potential which is 0 inside and infinity outside, you just make chaos. And 0 if z is less than right edge and more than left edge, right? And infinity if it is either bigger than left edge or smaller than right edge, right? And then you are just solving time in dependent Schrödinger equation. Well, part of this solution can be done right away if you know that potential is infinite. it means electron will never penetrate there. So at original space, Z larger than L or Z smaller than 0 outside of the box, wave function will be 0 for sure. So we have substantial number of solutions ready. The only question is what will be in the range between these limits. How do we solve these equations? What is dictated by differential equations?
Can we integrate?
Well, yes, but I'm going to, well, today there is no time, but when we meet again. There are a special class of problems in differential equations when equation itself is easy, it's really solvable, you get the function. But you have limitations. So although there is a class of functions that will satisfy equation, you have limits on the boundaries, so-called boundary conditions. So we need to make sure that the wave function at the edges will be 0. Right? So this is the complication, and the solution is obtained by superimposing several general solutions with uncertain coefficients until superposition with the match of the coefficients will make them equal 0 at the edges. And 0 is not general. Sometimes you have different boundary conditions. So you'll hear this term if you deal with differential equations. Okay, this is pleasant exercise, but with your permission, I'll skip. I'll just explain what it is. Generally, if you solve differential equations, the simplest thing to check is to plug in exponential with unknown power and see how this power will match the equation. So if you plug this solution into our time-dimensional equation, take derivatives, we will get that in order to have positive energies, we know that energies must be positive, and they should increase if momentum increase. But we will formally get that energy has negative sign. So energy can be positive in spite of this negative sign only if this parameter is imaginary. And from this consideration, one is obtaining that solution is imaginary exponential e to the power I some k, right? Which we already guessed for last month. That wave function is always imaginary exponential, but one can come to this point again just from plugging in exponential into Schrödinger equation. It's a property of an equation. Now, in our free space, solutions were traveling waves, traveling forward, traveling backwards. Can traveling wave be 0 somewhere? No. But if we add together 2 traveling waves, you already know standing waves do have some 0 points, right? So this is the main idea. So if we superimpose traveling waves going into the opposite direction, we can match boundary conditions. We can find such solution that will be 0 on the edges of the box. So the idea is to put unknown coefficients, C plus and C minus, in front of these 2 traveling waves and find at which values of unknown coefficients and the momentum or the wave vector, it will match the boundary conditions. So, time is running. I'm already out of time. I'm borrowing a couple of minutes from you, but you'll be done in slide or 2. So, we already know functional form. It will be exponential. But we do not know 3 things. We do not know k, we do not know c minus, and we do not know c plus. We need to find such coefficients, k, c plus, c minus, to match the boundary conditions. Yes, here's the last slide. And this deals with most challenging equation of your homework that I will be explaining today, in addition to preparing to your presentations at the evening session. So if we find equation as a superposition with exponential, we can replace each exponential according to our old body Euler, plus and minus sign. And then one can reshuffle these four terms in the following shape. Cosine with summation of this plus and minus coefficients. I sine with subtraction of these coefficients. If we pursue this form, it will be really possible, really easy to match boundary conditions. But for the sake of time, I am announcing end of the meeting and looking forward to see you today at 5. At B 132.
What did you say the number of the quantum chemistry classes next semester?
It's 476. There will be no graded homeworks on the projects, and getting high grade in computational chemistry is so much easier than in this course.
Is it possible to go a little bit early to tonight's session? Because we have Chem Club at 6, so I was thinking maybe we could.
Please, I'll try to come earlier, but if I'm not there, you can just sit and practice. The room is available.
Okay.
And
Cool.
I probably will come myself earlier just to prepare.
Okay.
I will not present and explain.
Yeah.
I plan to be there.
Okay. So I'll probably go on.
Probably right after that.
Yeah.
Yeah.
Oh, shoot, I missed the meeting.